This is a video overview of the MinSegMotor DC motor system. We'll start by going over the different elements of the hardware, then doing a review of some of the curriculum that's available, and then show some of the demonstrations. The hardware uses a Raspberry Pi RP2040, so it's the same that's in the RP2040 Arduino Nano Connect. It will appear just like an Arduino does, so nothing about the programming or interface is any different, just the form factors here has changed to make it smaller. For the motor, it has two headers for two different motors with encoder support. It's got a dedicated chip to count the encoder counts. It has a potentiometer. We have some labs where a student can turn the potentiometer and make the motor disc move and follow the tracking of the potentiometer. There'll be other headers on the final product that allow different motors to interface to do different labs. The nice part about this is a lot of these parts are 3D printed, so the hub, they're all clearance fit, so it's really easy to move and make different attachments. You can have systems with a fast time constant. This is a weighted disc. Lots of heavy washers in here. So this has a very large time constant if you want to do that, systems like that. And of course you could do even larger ones. This is nice because it allows you to do systems where the time constant is about 42 milliseconds up to a system where the time constant is 1.6 seconds. And that drastically changes the nature of the control design problems because the ratio of the speed of the system versus its control actuation magnitude is much different. So it's much more challenging control problem. So all of these different inertias and time constants are available. And the nice thing for student labs is you can keep constantly changing your plant every semester to get different numerical values to keep the labs and the values fresh every semester. And these are all for traditional DC motor labs. And then it's easy to add a pendulum to the system. Oops. This one hasn't been pressed on yet. It's a little tight at first, but easy to add a pendulum to the system to do simple pendulum labs. So now you do your 1D nonlinear system and do the linearization and control for a system like this. This has to be on the edge of a desk. So there's a clamp that slides in, and then you'll clamp this whole thing on the edge of the desk so that the pendulum can move back and forth like that. So now we can go back to normal DC motor. So we can go from DC motor to pendulum quickly. And the future kits, which is the current version that's being worked on, has the ability to go from a simple DC motor to a pendulum, and then the last thing will be the addition of this small encoder on top, so you can do a three-dimensional rotary inverted pendulum, and this will plug in the back there. So that's the overview of the hardware and all the different capabilities that are planned from basic DC motor control labs, 1D nonlinear pendulum lab, full 3D rotary inverted pendulum system, all with the same hardware and a small, easy-to-use form factor. On to the software, or the curriculum. This particular motor is used in our control systems lab, and I can share all of these different labs. We have six labs. Each one has a pre-lab, an experiment I do in class, and a lab submission. The first lab, solving ODEs. Actually, if I share this, you can see there'll be a lab summary that will describe what each of the labs cover. Solving ODEs, modeling a DC motor, so it's doing voltage, current measurements, and getting a step response for K and tau, frequency response, basics of feedback control, position control, and speed control. These are all the different labs. There'll also be some sample results. You can kind of see what data we can expect to get from these different labs and how well that data can match theory. The first lab is just solving ODEs, so these are just the labs that are really hardware intense. And the first lab is doing parameter ID, so doing voltage and current measurements to estimate parameters like KB and R, and then determining the transfer function from the motor parameters. Then getting the step response, getting K and tau from that, and then comparing those two. And depending on how well, so this is all just sample data, so they can vary depending on what data you're doing and what experiments. But here we can see that, of course, the experimental is the one with a little bit of discretized noise. The black box will always match that fairly well because we're just curve fitting the step response. Then depending on your measurements and if anything in the system changed, your physics base could be further or closer away. So that's how well we can get a match, and that's some of the parameter ID for lab 2. Then lab 3's frequency response. This shows the input-output sine wave versus time. And then from this, we have them manually extract out the delay to calculate the phase, manually extract out the magnitude to get the magnitude, summarize all of this. So they'll do this for a bunch of different sine waves. By hand, calculate the time shift to get the phase, the magnitude, and then construct the experimental Bode diagram. And then compare it to the lab that they got in lab 2 to see how well that matches theory, and it does a pretty good match. In magnitude, pretty good match in phase, of course, up until the higher frequencies where the delay in the microprocessor is going to start, dropping this down exponentially. But pretty good match for the Bode diagram, experimental Bode diagram. And labs 5 is proportional control, position control. And for that, we can just use, because it's a type 1 system, we can just use proportional control to get pretty good response. Here, this is for low gain. For low gain, we see that because there is significant Coulomb friction, I probably should have included a slide that has some of the ramp response, because there is significant Coulomb friction in the system. So if the gain's really low, that Coulomb friction will cause a significant amount of error. And once we characterize that Coulomb friction, which is also done in lab 2, you can estimate, and that's what students do in this lab, is they'll estimate how much error they actually expect the real system to have based on that Coulomb friction. So they'll be able to say, oh, we have 30 radians of error, and I expected that based on the amount of Coulomb friction I had. So it doesn't have a good match to theory because there's that nonlinear Coulomb friction. At higher gains, as long as you have a large enough step size, at higher gains, that Coulomb friction is not much an issue. And here we still see that the theory versus the actual experiment doesn't match well, because once it gets close to that desired position, that Coulomb friction stops the motor from turning. So it's reasonable transient response, except for when the error gets small and the motor just turns off because of that dominating Coulomb friction. In this lab, they don't add any techniques to get rid of that Coulomb friction. And I think when we do the last lab, we add in that constant voltage to get rid of the Coulomb friction. But the match is kind of what we expect, and the error, even this percent overshoot error, can be calculated ahead of time, and they can prove that we get this kind of error. And then we can do the maximum gain without having saturation, and it gets a better sort of transient response. But again, once the actual motor, the error in the actual motor gets small enough, it just turns off. So we have not a great experiment versus theory, but when it's not great, we can actually predict why it's not great because of the presence of that Coulomb friction. Again, in this lab, they don't do anything with that, so you could get rid of that Coulomb friction or handle that Coulomb friction to get better results. Then the last lab is speed control. This is where we demonstrate, we get rid of that Coulomb friction in this lab, and we demonstrate a better match to theory because we've taken care of that. So the first one is doing proportional control for speed. So speed is a first order transfer function. So that's a type 0 system. It's going to have steady state error. For proportional control, that's what this first graph is proportional control. And they predict how much proportional control, or how much error that is for proportional. You can also see that the settling time is around 0.3 seconds. So then they add a pure integrator to get rid of the steady state error. And of course, as soon as you add an integral term in your compensator, steady state error goes away. We have a great match between experiment and theory. We're also getting rid of that Coulomb friction by adding a half a volt to the control effort. But now we can see that the settling time is 10 times longer. It went from 0.3 seconds to 3. So to recover some of that speed that was lost by using a pure integrating compensator, we add derivative control or a 0. So this is now a PI compensator. Now the PI compensator can get some of that settling time around, it was 0.3, now I can get it back around 0.5. So this is your PI compensator for speed control, and there's a pretty good match between experiment and theory. So this is all what the hardware characteristics are and how well it matches theory, and when it doesn't match theory, explaining and calculating what kind of error that's expected from those non-ideal things, namely Coulomb friction, matches fairly well. So it's a really great hardware system for demonstrating different aspects of both ideal and non-ideal characteristics for a DC motor. So that's summaries in here. And again, all these labs can be available. There are the lecture notes for all 6 of the labs that can be available as well. And they're just examples that we go through for each of the lectures. I also have and these are just the bare minimum to do the lab. And I also have some video lectures where I'm going through some of this content. These are live videos during class, so the volume and sort of audio characteristics are certainly not great because I tend to over project during lectures, but they're there because they might be useful to help quickly learn the material in the lab and see how I go over those different concepts. The last thing is the demonstrations to kind of get started quickly. All of the basic get started stuff is in Simulink. Working on Python and Arduino codes that mirror this very well, but that code, the Simulink code, is pretty clean, but the Arduino and Python code isn't exactly up to standards. I can share that, but it's definitely messy and it's not my preferred, in its current form, it's not my preferred style to distribute though. Of course I can share that. So here all the hardware is going to come with just a basic demo that reads both encoders if they're present, and turns both motors on if they're present, and different I/O that's on the board that can read the potentiometer and turn the LED on and off. So this is running, and I can now see that if I have a motor on here, you can see that the motor's rotating back and forth, and I'm reading it. So I always have a demo file. It's good to have everything turn on and off so you can debug your hardware. Next lab that can be available is position control. Position control is type 1 system, so it won't inherently have any steady state error, which means proportional control should work fairly well for this system. So let's take a look at this demo. The Simulink takes a little bit for the code to get going, but we'll get the code compiling, take a look at the system. It's going to do a reference from 0 to pi. It's using a proportional gain of 1. So if we have pi is 3 radians approximately, we multiply by 1, that's going to give us 3 volts. So we're going to be below the saturation voltage. So this is a pretty reasonable gain in terms of magnitude for the amount of error that we have. A lot of the labs, you have to be really careful about the design of experiment, meaning how large does your reference need to be. So you have a command signal that doesn't saturate, and it needs to be large enough so that the Coulomb friction isn't the dominant physics in the system, so you get a reasonable looking response. And that's what's nice, is all those numbers and magnitudes have already been done already when you have a system that has the curriculum developed. So it's going to be position control. You see that there's pretty significant error from that Coulomb friction, but this is the response. And we can calculate again what that error is. If I start increasing this gain, we'll get better steady state error, but more overshoot. So that's simple position control. And then we'll take a look at the speed control. And this will be the PI. We have them walk through proportional, then pure integral, just K over S. And then adding that derivative term to recover some of the lost speed. So now here we're going to be doing the compensator in whole zero gain form, K, S plus EC over S. It's written out in kind of easy block diagram form. Here we can see we're adding half a volt. That's to get rid of that Coulomb friction. We're only doing from 0 to 155. This technically should be positive and negative depending on the sign of the voltage that's going to be applied, but this works considering the references are always positive in this case. We will get this going. And again, this is going to be speed control from 0 to 155 radians per second. In these later labs, in the earlier labs, we have them see the encoder and the motor blocks separately so that it doesn't always look like it might in their control classes. They have to think about the control on the equations a little more. And in the later labs, we put them all in a subsystem so that it's a little closer. In the later labs, we want everything to look as close to the theory as we can once we've walked through all of those different non-ideal things, make the block diagrams, start looking closer to what they would have in their theory classes. So now we'll do the speed control, and this will match theory very closely because we're getting rid of that nonlinear Coulomb friction term. So that's the speed response. Again, it's pretty well. It gets rid of the steady state error, matches well, and it matches theory well. Those are all the basic labs we can do. If we look at this subsystem, it's motor driver and it's reading the encoder, calculating the derivative to get speed instead of position. So that's the overview of the hardware, the curriculum that I can provide and post, and a couple of the different demos to get started. The Python Arduino code is going to be worked on and improved so that it matches kind of the structure that's presented in these block diagrams, so that if you go through these demos and learn them, and picking up the Arduino or Python using these block diagrams for learning is a nice, easy transition.